Hello everyone, my name is Jose Gibojo. I'm here with Andrew Mays and Hale Holden. We're Team Raytheon, and we're going to be presenting our capstone project, the Digital Reference Hydrophone. A hydrophone is an electrical device that can translate underwater acoustic signals into electrical signals. What motivated this project was the need for a smaller, more efficient system capable of testing multiple hydrophones, and therefore reducing the time and money cost to debug these devices. To meet the requirements of our best anticipated outcome, we needed to filter the signal, have an external trigger, produce a test tone, have a user-friendly interface, and being able to plot the FFT of the data. Here you can see a block diagram of the whole system, from the hardware section to the FPGA to the software section of the project. For the hardware section of the project, I started by defining the function characteristics and designing the block diagram. From this block diagram right here, you can see that the hardware section is divided into three main stages. Stage 3, which has additional gain to the signal. Stage 2, which is composed of 3 active low-pass filters and an amplifier circuit. And Stage 1, which is composed of 4 active bandpass filters and a test tone. The hardware section also needed to provide power to the FPGA as well as all the analog components of the system. The key accomplishments from the hardware section were defining the function characteristics, designing the block diagram, designing the filters for Stage 1 and Stage 2, simulating the filters, and the schematic capture. Here's a picture of the schematic capture in which each of these green boxes represent a subsheet of circuits. Here you can see a simulation of the whole path, from the hydrophone to the ADC, which connects to the FPGA. For the PCB section of the project, we were able to get all the parts we needed, design the footprints, and finalize the layout. Now, Andrew Mays is going to talk about the FPGA section of the project.
Over the past year, I worked on the firmware side of this project. This included block diagrams, setting up a programmable system, state diagrams, implementing VHDL logic, and also simulating the VHDL logic. As you can see here, this is a block diagram of the ADC interface, fixed-to-float converter, and our ping pong buffer. I also made other block diagrams. For example, this is for our test tone. The reason we had so many block diagrams was to verify that all the functions of our device were accounted for, and it also created a seamless transition into our state diagrams. So we use state diagrams to show the progression of our FSMs. It also shows which signals will be asserted in each state, as well as which signals cause the transition. This here is our ping pong state machine. The way the ping pong state machine works is it reads in all of the parameters from the software, uses those to write samples into the buffer, as well as at the beginning of each buffer writes a header. The header includes the user tag, the operating parameters, the number of samples in the buffer, as well as the running sample count. The other thing the ping pong FSM does is it asserts a flag to the software to let it know that a buffer is full. This can be seen in the simulation. The simulation was done in Vivado. Each VHDL module was simulated individually. However, this is a simulation of the full test tone path. As you can see, the address is being incremented as each sample gets placed into the buffer with a write enable. You can also see down here where the hardware indicates that a buffer is full, switches banks, and tells the software that a buffer is now being ready to process. And finally, this process will continue until the parameter of capture end is met. And finally, here's Hale to talk about the software.
So during my tenure on the software side of this project, I was tasked with first creating, of course, the paper design and then actually implementing it in both Java and C. This included, for example, the UDP server on the embedded system board, the UDP client on the PC, the Java application on the PC that ran the client, and the script within the Java application that would take all the parameters supplied by the user, send them down the hardware. Here you see a heavily simplified block diagram of the software. You could zoom in on the real thing for days, you'd never figure it out. So this was used for reference while developing, so you actually had context for where everything fit and how it all interacted. So you stay within spec and within scope. Programming the C for the board was done on the Xilinx software developers kit, which comes with a terminal emulator, so you can see all the printfs from the board over TTY in plain English on your PC. Here you have Wireshark. Up in the top there, you can see a fragmented IP frame because the PBuff was not able to sit within a single frame buffer of the Ethernet, which, by the way, for our purposes, was the network interface we were connected to. This, of course, is very informative, makes things very easy to debug because you can see hexadecimal character by hexadecimal character exactly what is contained within an individual PBuff. For example, again, you can see this is a data packet. You can see the header, third line down on the right. And here you see the JSON config file used by the script to load in all of those user-supplied parameters. This, of course, eventually determines exactly what the hardware does. At the last minute, last night in fact, I managed to build up a mock-up of a graphical user interface. This is actually functional. You can load that JSON manually and manually run the different commands down to the hardware yourself. And you can even change these parameters in these text boxes. There's also an analog clock. And just as a sneak peek of what the demo is going to look like, here's one of our graphs. This is a LFSR pseudo-random used as a test tone. We oversampled 4 times to get this little waveform here to show the rough accuracy of it as a pseudo-random generator. And we'd like to thank everybody who contributed and helped us on the way.